My name is Abdul Qadir Mahmoud and I'm from Delft University of Technology. Today I will present to you my paper which is about embed data parallel spin wave logic gate. To the brief introduction about spin wave, then I will move to the explanation of the spin wave basics. After that I will discuss the proposed structure of logic gate. Then I will show the simulation results and the comparison with the conventional approach of logic gate. And in the conclusion I will sum up. The information technology revolution society experienced during the past decade resulted in the generation of a huge amount of raw data which their processing require efficient computing platform. So far, CMOS downscaling was able to meet these requirements. However, due to different technological issues, CMOS downscaling turns out to be more and more difficult, which indicates the close end of Moore's law. In view of this, different technologies have been considered as CMOS alternative to meet the data processing market requirements. Among those, spin-wave-based technology stands apart as a promising alternative avenue because of its wavelength, which can reach down to nanometer. Its frequency can reach up to terahertz. It has ultra-low energy consumption. It has an acceptable delay. It has an intrinsic data parallelism feature. The paper contributions can be summarized as follows. The design of multi-frequency byte-wide inline spin-wave logic gate, the validation of the proposed structure using micromagnetic simulations, comparison of the design with a conventional approach, which stated that the proposed majority gate requires 4.16 less area than the conventional approach of logic gate with a similar latency and energy consumption. Magnetic material is exposed to an external magnetic field, the electron will start spinning around themselves toward the external magnetic field. This spinning behavior can be described using Land-Luft-Torque equation. Now, if this electrons is deflected by means of the magnetoelectric method or antenna or another method which excite the electrons, then the electron will start spinning while interacting with the electrons beside them by means of the exchange and dipole-dipole interactions, which will result in a spin wave. A spin wave can be characterized using wavelength, which is the minimum distance between two electrons that exhibit the same spinning behavior, the wave number, which is the number of waves per cycle, and the phase. Here is two examples of different cases where the phase is 0 and the wave number is 1, and with a phase of pi and the wave number of 3. Now we saw the spin wave. We want to know how we can benefit from this spin wave to establish the spin wave based computing. The main principle of the spin wave based computing is the wave interference, where if two spin waves that have the same phase interfere, then they will interfere constructively, generating a bigger wave. Whereas if the two spin waves are out of phase, then they will interfere destructively, resulting in cancelling the spin wave. Now, how we can benefit from the wave interference principle? That is established by the approach of logic gate, where n cells are used to excite n spin wave with the same frequency, and they are interfering in the functional region, and at the end the result of the interference is captured at the output cell. Now what if we want to process 8 bits? Then we need to replicate this structure 8 times, or the other approach is process them serially, which will generate area overhead in the first approach or delay overhead as in the second approach. Now spin wave enable the parallelism intrinsically. How is that? Side in different spin waves with different frequencies and the same waveguide without affecting each other, and the same spin waves with the same frequencies, they are interfering only and can be captured at the output. As you can see in this structure, M input in-bit data parallel spin wave logic gate. There are M input at n different frequencies, and only those who have the same frequency will interfere with each other constructively or destructively based on their phase, and the result will be captured at each frequency separately. Now, this structure has bent region which is not preferred using by spin wave, because spin wave is weak wave by its nature. Because that we propose the inline multi-frequency logic gate. As you can see here, all the inputs are excited in the same waveguide, and they are the spin waves of the same frequency are interfering with each other and not affecting the spin waves with different frequency, and are captured at the output separately. Now the distances between those inputs are important, and it is expressed in terms of the wavelength. They must be multiply of the wavelength of each, because each one has different frequency and therefore they will have different wavelength. Now the output location is really important as well, because if the distances are n multiplied by lambda, then that will make the output detection will detect the non-inverted version of the spin wave. However, if the inverted version of the spin wave is required, then they must be placed in n plus half times lambda of the last input cell of the same frequency. That we show the proposed structure. We need to show the validation of such a structure using the micromagnetic simulation, because we use the following parameters which are fed to the object-oriented micromagnetic framework to simulate the structure and validate it. Now we extracted the results from the object-oriented micromagnetic framework, and they are post-processed using MATLAB. And as you can see here, each bits which have different frequency, they are propagating in the waveguide without affecting each other, and only the spin waves with the same frequency, they are interfering with each other. As you can see here, by taking the FFT, we will show the frequency component. As you can see here, each case we excite 8 parallel bits in the same waveguide with different frequencies. And as you can see here, of each case you can realize 8 different components, which means that we have 8 different spin waves with 8 different frequency on the same waveguide, and the spin waves with the same frequency only interfering with each other. Now, to make things more clearer, we showed each component separately. As you can see here, the 3 inputs are 0, 0, 0, which means that the spin wave has phase of 0. However, if the input is logic 1, then that means that the spin wave has phase of pi. Let's examine these simulation results. As you can see here, the input 0, 0, 0 will generate in the majority gate 0, which is this one. While The inputs, when they are 1, 1, 1, then they will generate output with logic value 1, which means spin wave with phase of pi. As you can see here, the both cases are with pi difference in terms of phase. Also, the other cases can be referred to as in the same way. For example, 0, 0, 1, which generates logic 0, as you can see here, it has the same phase as the first case. However, 1, 1, 0, it has the same phase as the last case. The same thing occur on the frequency 20, 30, 40, until 80. Now, to see the potential of such an implementation, we compared the proposed logic with the conventional one. While implementing 8-bit, we replicated the majority gate 8 times while we implemented it only on the same, using the same structure, using our proposed parallel structure. The two implementation styles exhibit the same delay and energy consumption as they use the same number of sources and detectors. However, the conventional approach consumes 0.116 micrometer square, while the 8-bit data parallel gate requires only 0.0279 to implement the 8-bit majority gate. That means that the proposed approach requires 4.16 times less area than the conventional approach, which shows the importance of such a implementation. Conclusion: a novel data parallel multi-frequency spin wave structure has been proposed. The results were validated by object-oriented micromagnetic framework. In addition, the proposed structure was compared with the conventional spin wave gate, and the results show that the proposed gate provides a 4.16 times area reduction than the conventional one without inducing any delay and power overhead. Thank you for listening and for your time. That's bring me to the end of my presentation. Thank you.